The universe should be dark, vast, silent, and endless, a void untouched by memory. And yet, hidden within this silence, there lingers a glow, so faint it can barely be seen, so ancient it should not still exist. It drifts across the cosmos like a ghost, older than galaxies, older than the first stars. A remnant of an age when the universe was fire, when matter had only just begun to cool, when time itself was still learning how to move forward. By every law of physics, this light should have vanished long ago. It should have been scattered, drowned, erased in the turbulence of creation. But it persists, a quiet defiance against everything we think we know. Scientists call it the afterglow of the beginning. But within its fading patterns are contradictions too sharp to ignore, alignments that point in directions no theory can explain, whispers of order in what should have been chaos. Some of its photons seem impossibly old, as though they predate the very structures they illuminate. This is not just light, it is a paradox, a message that should not be here, a riddle that unsettles the story of creation itself. If the universe has rules, why does this glow break them? If time has a beginning, why does it speak of something older? A silent, haunting ember travels still, carrying secrets from before the first star. The ancient light that should not exist, and yet does. The first hint did not arrive with fireworks, but with a hiss. High above a New Jersey meadow, a pale aluminum horn faced the sky. It had been built to listen to whispers, faint radio murmurs from Earth-orbiting satellites. Yet the instrument heard something else entirely. No matter where it pointed, the sound remained, thin, persistent, and curiously uniform, as if the whole sky exhaled the same breath. Engineers Arno Penzias and Robert Wilson cleaned every bolt, traced every cable, quieted every source of earthly interference they could imagine. Even the pigeons that had made a home inside the horn were evicted, their presence reduced to a polite euphemism, a white dielectric material, and removed by hand. The hiss, however, refused to leave. In that stubborn noise lay a relic from an age before any star had burned. The signal did not diminish when the horn swept from horizon to zenith. It did not swell when the Milky Way climbed the night. It was everywhere, the same in every direction. A soft frost coating the sky at a temperature a few degrees above absolute zero. When the news crossed town to a Princeton group led by Robert Dickey, already hunting for the very glow predicted by George Gamow and colleagues, the meaning fell into place. This was not local static. This was the afterglow of a universe once incandescent, now stretched and cooled by expansion until its fire had become a faint microwave fog. Penzias and Wilson had tuned, quite by accident, to ancient light. A paradox took shape in the silence that followed. If the cosmos began in a furious heat, there should be a remnant. Photons released when the first atoms formed and the fog of plasma turned suddenly transparent, racing outward ever since. Theory said these photons ought to flood the sky, exquisitely uniform and chilled by time. Observation now agreed. The universe itself had become a backdrop. The sky was no longer black, but gently luminous with memory. The signal's temperature, just under 3 Kelvin, would soon be measured more precisely, its spectrum tested against a perfect blackbody curve. It fit with unnerving perfection, a match so exact that it left almost no room for alternative stories. A fireball had cooled. Time had kept a receipt. Yet in that perfection another question stirred. If this light came from everywhere and from the same early moment, then the cosmos across vast distances must have shared its temperature almost exactly. But how could that be? Regions now separated by billions of light years should never have been able to communicate, No signal could have raced fast enough to even out their temperatures before the glow was released. The uniformity of the ancient light solved the riddle of a hot beginning and opened another at the same breath. A horizon problem written in faint microwave ink across the entire sky. The hunt for finer detail began. In orbit, above the tremors of weather and the fog of human radio, a new observer was prepared. Launched in 1989, NASA's Cosmic Background Explorer, COBE, carried two instruments destined to become quiet landmarks. One, the far-infrared absolute spectrophotometer, would test the spectrum of the background with almost ceremonial rigor. If the universe had ever been perfectly smooth, no structures could have formed. If it had been too rough, the cosmos would look nothing like it does. Somewhere in the ancient glow, the right amount of imperfection had to be encoded. COBE's verdict was austere and startling. The spectrum of the background was a near-perfect blackbody, the best such curve ever measured in nature. It was the signature of a true thermal relic, not the echo of some later astrophysical process. And yet, sitting on that immaculate curve, the radiometers revealed the faintest mottling, temperature fluctuations at the level of tens of microkelvin, the first contour lines on a map of everything. Those ripples were not random noise. They were an origin story. Quantum tremors inflated to cosmic scales, gravity's first footholds, the blueprint from which galaxies would rise. The sky's grain had finally been seen, but the story of the glow refused to stay simple. Better maps would be needed, maps that could sketch the entire sphere with sharper eyes, tracing the earliest fingerprints of structure with a precision COBE could not reach. In the early 2000s, the Wilkinson Microwave Anisotropy Probe, WMAP, drew a new cartography, color-coded ellipses draped over an entire celestial sphere, a heat map of the first light's whispers. The data refined the age of the universe, the proportions of its contents, and the strength of the primordial ripples. And beneath those triumphs, the maps carried something disquieting. Large-scale features that did not sit comfortably within statistical expectations. Alignments of the lowest multipoles, vast, gentle waves across the sky, seemed to favor particular directions. It was an unlikely neatness, so persistent that cosmologists gave it a wry, uneasy name, the axis of evil. The phrase was half joke, half confession. The background appeared too well aligned, as if mere chance had been unreasonably kind, or as if the universe kept a preference it should not have. Even in the language of caution, the unease lingered. Perhaps the alignments were artifacts, a quirk of foreground subtraction, a whisper of our solar system's dust, an imprint left by scanning strategies and beam shapes, or perhaps they were something real and uninvited, a hint that the earliest stage of cosmic history left an anisotropic seam in the sky. The Planck satellite would later sharpen the picture again, confirming the background's exquisite black-body nature and refining the ripples with even greater fidelity, while leaving the largest-scale oddities stubbornly resilient to easy dismissal. The earliest light seemed to carry both the comfort of order and the discomfort of patterns that should not prefer any axis at all. While background maps deepened, other forms of ancient light arrived from different directions in time. The Sloan Digital Sky Survey began to census the distant universe, finding quasars at redshifts above 6, beacons powered by black holes already massive a mere billion years after the beginning. Their light wove through a forest of hydrogen absorption, sketching the timeline of cosmic reionization, the era when the first stars and galaxies relit the fog. and implying that structure had organized itself with unnerving speed. Deep fields carved by the Hubble Space Telescope reached toward the first few 100 million years, revealing tiny galaxies whose existence pressed against the limits set by simple models of early growth. Each discovery felt like a question posed as light. How did the universe become so luminous, so quickly? Against this gathering of signals, the microwave background remained the most ancient, the most democratic. Every direction held its memory. It was the canvas on which all later light would be painted, the surface beyond which ordinary telescopes could not see. To gaze at it was to look as far back as photons could carry vision, to a time when neutral atoms first formed and the cosmos lost its opacity. Yet the background's simplicity cloaked a layered complexity. Within its uniformity, ripples. Within its ripples, correlations. Within those correlations, whispers that tugged mathematicians and physicists toward the edges of their models. Non-Gaussian hints, large cold spots, alignments whose very existence demanded humility. What began as a stubborn hiss in an aluminum horn had become a geography of first light. It taught that the universe is older than any star, that it once glowed everywhere with the same heat, that its earliest imperfections were as delicate as breath on glass and yet heavy enough to become clusters of galaxies. It also taught that the sky holds curiosities that refuse to be smoothed away by better instruments or longer integration times. The background, so named for its evenness, had a personality. The story of discovery threaded people to machines, theory to patience. Penzias and Wilson cleaning the impossible silence. Dicka, who turned from the phone and told his team, with dry understatement, "Well, boys, we've been scooped." COBE, orbiting high and slow, distilling a spectrum that could have been drawn by mathematics alone. WMAP, unfolding a sky where ancient breezes had left their swirls, and beyond them, a flotilla of observatories listening in other bands and other epochs, quasars as lighthouses, galaxies as clocks, starlight as testimony to how swiftly the dark learned to shine. With each step, the ancient light proved itself both narrator and critic. It narrated a hot beginning, a rapid cooling, a universe that spread and thinned until atoms could hold on to their electrons and photons could finally run free. It criticized any story too tidy, offering in its low harmonics a waver of doubt, a note off-key. Older not in absolute age, the age was written in the spectrum and measured in its waves, but in character. Too organized at the largest scales. Too swift to build lighthouses at the cosmic dawn. Too precise a match to a thermal curve to be anything but relic fire. And yet too full of teasing asymmetries to be dismissed as mere statistical play. The ancient light, meant to be a background, kept stepping forward. It is tempting to make the discovery feel inevitable, to retell it as a straight line. Prediction, detection, refinement, triumph. The real path bent through doubt, instrument quirks, foregrounds that masqueraded as cosmology and cosmology that disguised itself as noise. Each time the map sharpened, the cosmos gave a little more and withheld a little more. In the hush of data, scientists learned to hear both the chorus of agreement, the way theory and measurement sang together, and the quiet solos of discord that might yet ask for new physics. The first glimpse, then, can be given its proper name. Not a calendar date, not a single eureka, but the moment the sky ceased to be empty of meaning. In that moment, the darkness of space turned out to be luminous, thinly, perfectly, and imperfectly all at once. If the glow is uniform, How did such distant regions agree on a temperature before they could talk? If the largest patterns align too neatly, what hand drew the ruler? If the earliest quasars burned so brightly so soon, what engines were already in place? The chapter ends where the mystery truly begins, with light that appears to follow the rules with breathtaking devotion, and at the edges of those rules, a persistent suggestion that the universe may be more intricate than the equations that first called this glow into being. The first glimpse of the impossible was not a contradiction shouted. It was a whisper that did not fade.